Yeah, this topic is rapid separation of protein on superficially porous particles, so-called SPP. Um, so far, we only considered the columns are packed with silica, the fine particles, and then the surface may be bonded to other groups, yeah, to impart special properties, yeah. But the silica, this silica particle itself, they are all porous, right? So you need a lot of much pressure to push the solvent through the column. But here, this superficially porous particle, superficially means that only the outer part is porous. Okay, so that's why it is called superficially porous particles. So this porous part is thin. Okay, it's quite thin. How thin? 0.25 micrometer thick. Okay, and on this 5 micrometer non-porous silica core. Now this is silica core. This one total diameter is 5 micrometers, but this thickness is very thin, right? So the solute don't need to diffuse into the core, right? But only it has a equilibrium within this thin layer. Okay, and here on the surface of this one, and then C18, the stationary phase bonded to the layer. Okay, so since this layer is thin, a mass transfer of solute into this SPP, right, is 10 times faster than fully porous particles. Okay, yeah. If you use this full porous particles, then mass transfer will be very slow, right? So there are features of SPP faster, yeah, as I said, faster mass transfer into thin layer, and it uh, don't require high pressure, yeah, because mass transfer is rapidly achieved and not very high pressure is not is required. Okay, and but low sample capacity, yeah? And since this is thin, so sample capacity becomes low. Okay, let's look at this chromatogram. Yeah, this is rapidly proteins are separated on superficially porous. It is octadecyl group attached to silica, right? So in the 2.1 times the 75 millimeter columns containing porous shell, that is one. Okay, so analyte could be angiotensin, neurotensin, yeah, ribonucleic insulin, such a the large the protein molecules. Okay, for separation of macromolecules like protein, this superficially porous particle is good. Okay, and also with liquid HPLC, the chiral drug separation, yeah, is possible. But in this case, you have to use the chiral stationary phase, like in gas chromatography, right? If you use chiral column, and then it's possible to separate, chiral molecules, right? Most drugs are chiral. Yeah, most drugs display chirality. Yeah? You know the chirality. Yeah? Chiral molecules are mirror images each other. Okay, let's on the surface of silica. Now you put uh, stationary phase. Okay, this bonded. This is bonded stationary phase, and it displays chirality. Yeah, RR. Okay, RR chirality here. Okay, and this naproxen. Yeah, it also this molecule also display chirality. This is S naproxen, and this one is R naproxen. Okay, and uh, this one they are optically active. Okay? This is optically active bonded phases. In other words, chiral stationary phase is needed to resolve enantiomers. All right, yeah. This one has some more interaction with this one, and this one has this chiral bonded phase have a strong interaction with this R naproxen. All right. Now this is a modeling. Okay. Let me see. And this is a naphthalene. This is a naphthalene group. Naphthalene here. This is this is naphthalene. This is naphthalene group. Okay. And this one, let me see. This is dinitrophenyl group. Dinitrophenyl. Which one is dinitrophenyl? And let me see. Dinitrophenyl group. Hey, yeah, this is naphthalene group. Yeah, this is the bonded phase. Okay, and R naproxen here has a less stable adsorbate. Okay, but S naproxen is strongly adsorbed on this SS this bonded phase. Okay, so since the interaction energy between this bonded phase and this R naproxen and S naproxen are different. Yeah, so chiral separation is possible. Okay, and now let's consider the elution process. In adsorption chromatography, competition between solvent and solute molecules for the site on the stationary phase. Okay, and solute is dissolved in solvent. Okay, and now we use the eluent like in a mixture of organic and aqueous solvent. So uh, so the stationary phase site for the site, the solvent and solute molecules compete each other, right? Let's look at this one. This is solvent molecules, and these are solute. Okay, now it is adsorbed on the stationary phase. Okay, and this one is a stationary phase. Uh, we want to, only solute molecules are interacted with a stationary phase, but actually, these solvent molecules now compete with the solute molecules for the site in on the stationary phase. Okay, yeah, and this one now solvent is the flow. Okay, this is flow direction, and here now let's this now this adsorbed solute molecules may be replaced by these solvent molecules. Okay, yeah. The relative abilities of different solvents to elute a given solute from the adsorbent are nearly independent of the nature of the solute. Okay, and elution occurs when solvent displaces solute from the stationary phase. Okay, yeah. If the solute molecules are absorbed on the stationary phase for a long time, and then separation cannot be done. Okay, anyway, these solute molecules must be replaced by the solvent molecules. Yeah, that is called elution. Okay, that's why the separation is done. Okay, yeah. So here the relative abilities of different solvents, yeah, to elute given solute here are nearly independent of the nature of solute. Okay, yeah, that's important. And next topic is no the yeah, let's temporarily stop. Let me see. Yeah, Eluotropic series of solvents ranks solvents by their relative abilities to displace solute from a given adsorbent. Okay, so here again in this figure, now these solute molecules absorbed in a stationary phase must be replaced by the solvent molecules, right? And solvent molecules, their eluent ability is very important. Okay, so we can people to make this table. Eluotropic series and ultraviolet cutoff wavelengths of solvent for adsorption chromatography on silica. Okay, and this eluotropic series of solvents is the relative ability to displace solutes from given adsorbent. Eluent strength is a measure of the solvent adsorption energy. Okay, value for pentane is defined as 0 on bare silica. Okay, here look at that. The first column is the solvent. Okay, pentane, hexene. Yeah, these solvents are used in HPLC, and eluent strengths epsilon 0 arbitrarily people assign the pentane to 0. Okay, and then if you use pentane as the eluent, and then this ultraviolet cutoff is 190 nanometers. Okay, and let me see, the hexene, the eluent strength is 0.01. Okay, it's a little bit more stronger, and like that. And the heptane, trifluoroethane, and like that. Okay? And methanol, the eluent strength is quite high, right? This is quite polar, right? This pentane is quite non-polar. Okay, eluent strength. Okay, and the more polar the solvent, the greater is its eluent strength. Okay, here, methanol, yeah, is more polar than the propanol. Okay, than acetone, like that. So this eluent strength is higher. The more rapidly the solute will be eluted from column. Okay, with this solvent with higher eluent strength. Okay, the the elution will be faster. Okay. Okay, let's consider the adsorption chromatography on bare silica. Yeah, we considered the two chromatographies. The first one is normal phase chromatography, yeah, which is the polar stationary phase is polar. Yeah, when you use polar stationary phase, yeah, that is a normal phase chromatography. Yeah. And so in this case, more polar solvent has higher eluent strength. Okay, and it is sensitive to small amounts of water in the eluent, yeah? Because the water is hydrophilic. Okay, this is a normal phase chromatography. Okay, you consider, yeah, you remember uh, in this chromatography, the polar stationary phase is used. Okay, but you know a reverse phase chromatography is often used. Okay, in this case, stationary phase is non-polar, and as a result, less polar solvent has higher eluent strength. Okay, eluent strength is increased by making the mobile phase more like the stationary phase. Okay, yeah. Reversed phase chromatography eliminates peak tailing. Yeah, eliminates peak tailing because the stationary phase has few sites that can strongly absorb a solute to cause tailing. Okay, so usually in a reverse phase chromatography, tailing phenomenon is smaller than uh, the in normal phase chromatography. Okay, but it is also it is less sensitive to polar impurities in the solvent. Yeah, because polar impurities. This is because non-polar stationary phase, right? And now let's consider the box 24-2, the structure of solvent bonded phase interface. Okay, this is the bonded phase. Look at that. This is the silica surface, and this is a bonded phase. Now we simply assume octadecyl bonded phase here. Okay, this one, this long, thick, black line. They are bonded octadecyl group. Okay, and then the thickness is 0.7 nanometers, and then here on top of that, yeah, there is adsorbed methanol monolayer. Okay, and this is you use methanol as a solvent. Okay, this figure illustrates the methanol and C18 interface. Okay, and in methanol there are solute molecules. Okay, now solute molecules now absorbed in the bonded stationary phase, and also is in the adsorbed methanol monolayer. Okay, yeah. And here, when you use acetonitrile octadecyl interface, and now is a mobile phase is acetonitrile. Yeah, acetonitrile is a solvent. Okay, here, and let's see. This is silica surface, and also this one, this layer is adsorbed acetonitrile pool. Okay, but in this case, in a methanol case, this methanol layer is simply monolayer. For acetonitrile solvent, this one is not monolayer. This is called pool. Okay, acetonitrile pool, and then thickness is much thick, 1.3 nanometers. Yeah, and then the solutes are in this solvent, and also in the adsorbed acetonitrile, this layer, and also in the silica surface. Okay, and then what? Structured layers of solvent at the interface between the stationary and mobile phases influence the separation in liquid chromatography. So situations are different, okay, depending on which uh, solvents are used. Okay, the separation becomes different. Okay, why? There will be different interactions. Okay, depending on the different solvent. Yeah, here let's look at that. Methanol eluent strength is very high, 0.7, but acetonitrile is 0.52. Yeah, and methanol and water, uh, this volume ratio, this one, yeah, usually the pure methanol or pure acetonitrile is are not used. They are mixed with water. Okay, and here on the left hand side, methanol water, ratio is 4 to 6 by volume, and here acetonitrile water ratio is 3 to 7 by volume. Okay, methanol, in the case of methanol, there will be a monolayer of methanol. Okay, in acetonitrile, not a acetonitrile monolayer, but acetonitrile pool. Okay, absorbed phenol, yeah, and caffeine molecules can reside inside this one, octadecyl layer, or on the outer surface of this octadecyl layer, or they can be dissolved in the here. Okay, so nitrile pool here. Okay, yeah, this figure illustrates that. Each type of adsorption site has a different binding energy and binding capacity, and affects the shape of the eluted solute band differently at different solute concentrations. So the interactions, yeah, interface structure are different. So the separation will be different. Yeah, this one illustrates that um, the choosing the solvent, okay, methanol water solvent or acetonitrile water solvent. Yeah, choosing solvent is extremely important in uh, HPLC. Okay, we'll consider this part in more detail. Okay, shortly. Okay, let's stop here.